Okay, so let me remind you what we were working on before break. I'll do another example as well. Here's our energy method. I've labeled it the energy method so far because there's still a major modification we need to make to it today. So we'll have the energy method in its final form at the end of lecture today. Now, what does it include so far? Well, it includes gravity. And gravity, what we've done is we've come up with another form of energy called gravitational potential energy. And it's kind of another energy bank account that it can be traded with. So we have the kinetic energy, which is energy due to motion. But when gravity does work, it trades with this other form of energy, which we call gravitational potential energy. So when gravity does positive work, as we learned, it increases the kinetic energy. Now we learn where it comes from. It comes from the potential energy. And when gravity does negative work and it removes the kinetic energy, we know where it goes. It goes into gravitational potential energy. So our approach here is to think of work as a transaction. Work is the process of energy transfer from one energy bank account to another. And energy conservation really just comes down to making sure that the energy is all there if we count up both bank accounts. So if in any problem, we tally up the amount of energy in the two accounts initially, we had better get the same balance in those two accounts at the end. Now in the equation here, you notice that work is not mentioned. Work is, of course, the transaction going between these. But our approach is to not sweat the multiple transactions that might be going back and forth between them. We just want to make sure the energy is all there somewhere. So we want to make sure that if the energy is not in one account, it's in the other one, so the sum of the two should be the same. So this is an extremely easy approach. We can have a problem where the energy gets sloshed back and forth maybe 12 billion times. It doesn't matter. But we just want to make sure the energy is all there at the end, same as it was at the beginning. Because gravity can only slosh it from one form to another. You can't just create or destroy energy. So we have our equation. Here's our kinetic energy equation. That's the energy of motion. You can figure out how much energy is in something's motion by taking 1/2 its mass times its speed squared. That's positive always. It can be 0, of course, I should say. You can have 0 kinetic energy. But it can't be negative, right? You either have 0 motion energy or you have some motion energy. And the faster you're going and the more mass you have, the more you have of it. And here's our formula for gravitational potential energy. That's how we keep track of that account of energy. It's the object's mass times g times the height. And we can also keep that 0 or positive if we choose a reference point that makes sure that's the case. So if we choose h equals 0 at the lowest height of interest in the problem, then the potential energy will either be 0 because we're there at that lowest height of interest, or it'll be positive because we're higher than that. So that's a very nice method because it allows us, first of all, nothing's a vector. Everything's just a number. And the balance of these two bank accounts is 0 or more. Just like normal bank accounts, although these days you can have negative balances, right? You can overdraw and stuff. These are not those bank accounts. So these can have either 0 or more than 0 in there. The transactions can be negative. Work can be negative. Work being positive or negative is just referring to whether it's an addition or a withdrawal from the kinetic energy bank account, right? If work is positive, it means you just got more kinetic energy. If work is negative, it just means you've got some taken out. But just like you can have a deposit or withdrawal to your bank account, no one can hand you negative $10, right? So the amounts in these two accounts are both positive or 0 at the least, even though the transactions can be plus or minus, okay? Now, this is not just a method that includes gravity. You also get a freebies of any force if the work done by it is 0. So we did an inclined plane problem at the end of last time before break, where I pointed out it's not just gravity, it's another force, normal force. But normal force always acts 90 degrees to the motion. and when force acts 90 degrees to the motion, its work is 0. I'm not saying the force doesn't exist, but it's what I call a guiding force. It's a force which plays a role in steering the object into a different path, but it doesn't make it go faster or go slower, right? It's not with the motion to make it go faster, increase the kinetic energy, do positive work. It's never more against the motion. Does negative work, makes it go slower. That's not what that force is about. It's a guiding force. So this method includes gravity, and you can have 17 different forces, but as long as they act 90 degrees to the motion at all times, they won't make it go faster and they won't make it go slower. The only reason you will increase your kinetic energy is because you got it from gravitational. So with that in mind, let me show you a problem where not only is it quicker to use energy, but the problem is so immensely complex that we had no hope of tackling it before we had this method. If we had to use forces, we would completely out of luck. Luckily, with the energy method, this is, by the way, my third example. I did the first two before break. This one, energy is not only going to be able to do it, but energy is still just as simple to use as it was before. Here's my problem. I have a roller coaster loop-de-loop. The roller coaster loop-de-loop, the initial height of this starting hill will be out here somewhere, 30 meters. I'm going to start a roller coaster car up there at rest. I'm going to let it slide down. It's going to go up and over this loop-de-loop. This loop-de-loop is going to have a radius of 10 meters, let's say. I know my drawing doesn't look like a circle, but let's assume it's a circle. It's going to go up over the top, down the side, and out the bottom. I guess I can label these points. I'll call them A, B, and C. And I'm going to ask, what is the speed at each of those points? BA, BB, and BC. I want to find them. They're not all the same, but I want to find them. So before I show you how easy this is to tackle with the energy method, let me show you how impossible it would have been to do previously. Let's say I were to tackle this with the forces method. Now, and I guess I should mention, this is a frictionless incline. So let's assume this whole thing is frictionless, because friction certainly can do work. It's not 0. And so we don't yet have that incorporated into the energy method so far. That's why it's called so far. So the only two forces that act on this roller coaster car are going to be gravity and normal force. Gravity, because we're on Earth, and normal force, because it's on a track. So gravity, during its journey, is, of course, nice enough to always point down. So no matter where this thing is, gravity pulls down. But the normal force is always perpendicular to the track. So that would look like this. Like that. So the normal force is all over the place. And if I wanted to find the net force at a given moment, I would, of course, need to combine, using vector addition, the normal force and gravity. So I need to combine these two forces to find the net force, which, of course, is changing at all moments. So that would be a brutal problem, even if I knew the exact shape of the track, which I don't. So pretty much, forces method is going to be way too hard. Okay? So that's why I would not want to do it with forces. Luckily, the work done by the normal force is 0. So at all times, the force from the track is perpendicular to the motion. So the normal force is perpendicular to the displacement at all moments. So it plays the role of a guiding force. It will never make the roller coaster car go faster. It'll never make it go slower. It simply makes sure that the track doesn't get smushed. The structural integrity of the track is protected. The only reason why it goes faster is because of gravity. And gravity, we know that we can track how much energy is in the gravitational form simply by tracking the height above the ground. So even though this goes through such a complicated path, the only relevant thing we really need to care about is how high is it above the ground. The active ingredients in these two energy forms are height and speed, which means that if you go lower, you go faster. If you go higher, you go slower. That's pretty much it. If you give up gravitational potential energy by going lower, you will have to put it into kinetic and go faster. Have any questions on the kind of general strategy before we go ahead and do this? Is there a question back there somewhere? No? Yeah?
Are there other kinds of potential energy besides gravitational potential energy?
Yes, so that's one of the things I'm going to talk about later today when I make a modification to this, is that there are many forces, in fact, I should say, where that you can do the same process, where you can come up with a potential energy form associated with them. And they're going to follow very much in the footsteps of gravity. But there are other forces where you can't do that. So we're going to separate those forces into those two categories. One's where you can form a potential energy and one where you can't. Are there any other questions before I proceed? Okay, so let me give you a sense of how I might do this. What I'm going to do is I'm going to make sure that the initial energy that this car has, this roller coaster car has, is still all there at point A. I guess I should say it should still be there at point B, and it should still be there at point C. The energy can't go anywhere. But let's start by saying whatever initial energy you have to have it all in at point A. So here's what I'm going to do. I'm going to add up my two forms of energy at the beginning and see how much I have to work with. So I have 1/2 mv initial squared plus mg h initial. And then I'm going to make sure it's all there at point A. If it's not in one form, it's got to be in the other. One thing you notice, before anything else, I guess I should mention, every single term has a mass. So what can I do? Divide both sides by mass and get rid of it. That's one of the major advantages of the energy method in its current form, is that everything always winds up with a mass. Then you can divide both sides by it and cancel it. You don't actually need to know the mass of the roller coaster car. Okay, so how much, at the initial point there, at the top of the initial hill, how much kinetic energy does it have? 0, because it's not moving. So all of its energy is stored. In fact, let's go ahead and set the set the reference height. I'm going to set h equals 0 at the bottom here because, of course, that's the lowest height of interest in the problem. It never gets any lower than that, at least that I care about. So what would I use for my initial height then? 30. So initial height is 30 meters. I guess I'll put that over here. H initial is 30 meters. What's the height at point A? 20 meters, right? You're at the top of the loop-de-loop, so your one diameter of the loop-de-loop above the ground. So if the radius is 10 meters, the diameter is 20, right? So I haven't given up all my gravitational potential energy yet, but I have given up some, right? If I've gone from 30 to 20 meters, there's some energy now not in potential. Where did it go? So if this quantity has diminished, where's the rest?
Kinetic.
In kinetic. So let's solve. I'll leave it to you. Just algebra, not physics. So you can solve here and you can find that the speed there at point A is about 14 meters per second. Okay? Now, did it matter that it went down first and then came back up? No, it doesn't. Remember? The only thing we need to track is height. If you go lower, you go faster. If you go higher, you go slower. Okay? So this is the kind of workforce problem that you should have down cold. It's all over your current homework, and it will be for sure on the exam. Question?
I noticed that A is like 20 meters. Wouldn't it be the same thing as B also? Because it's like even though it's lower, even though it looks lower on the in the loop, it's the same. It's kind of like the same height, right?
Well, this would only be one radius above
Okay.
the ground. This would be 10 meters above the ground. So A is 20 meters above the ground. B is only 10 meters above the ground. So at B, you're even lower, so you're going to be going even faster. In fact, all the calculations are going to proceed something like this. Just to not belabor the details too much, let me just label at each point, what's the height, what's the speed, and I'll put it the initial point, point A, point B, point C. So the initial height was 30 meters, and the initial speed was nothing. At point A, we knew that we went down to 20 meters, and we were able to solve. I guess I'll put numbers that we solved for in red, 14. We just talked about the fact that at point B, what's your height again at point B? 10 meters. So is your speed going to be bigger or smaller than 14? It's bigger. In fact, work it out yourself. Try it at home. And you should be able to get, just the same setup, you should be able to get that you're going about 20 meters per second. And yeah, it's not exact, well, it's taking a square root, but I'm just rounding. How about at point C? What's your height there?
0.
0. Okay, so all of the energy has come away from the stored form. It's all in kinetic, and of course, this is going to be your fastest speed yet, 24. So make sure you can solve for all of these numbers in red. They're slightly rounded off, so don't stress about that. Question?
Will we be getting problems where the height isn't that easy to see? Like it might not be like where B is, it's...
Oh, you mean like this loop-to-loop is kind of easy because it's the diameter of the radius?
Yeah, like, because B is at a 90-degree angle, so you can tell it's just one radius. What if it's kind of like...
Oh, yeah, if it's like here?
Yeah, something like that.
Yeah, I mean, that would be kind of annoying for sure. I don't think I would give you that one, just because that's geometry that, I mean, the hardest part about that would be geometry, which is not the focus of this class. For instance, the last example we did before break, we had something sliding down an incline, and then I expect you to realize how to calculate this height. That's just SOHCAHTOA. That's not that bad.
Okay.
And so you should be able to do things like that, maybe. The important thing is tracking height, right? So, but, you know, am I going to give you some crazy convoluted geometry where 99% of the difficulty of the problem is figuring out what the height is? Probably not.
Okay.
Are there any other questions on this? Okay, so really what I'm trying to hammer home is that the complicated trajectory here does not really matter. For instance, if I were right here on the initial hill I guess I should label my values. This was 14 meters per second. This was 20. This was 24. So those are, of course, just the sampling. How fast would you be going right here when you're sliding down the initial hill, but you're level with this point? How fast are you going right there?
20.
Nope.
14.
14. Same height, right? So you've given up the same amount of potential energy into kinetic. What about when you're sliding down this initial hill and you're level with the side here?
20.
Then you're going 20. Same height, same speed. What's it all about? Trading height for speed. How fast are you going right before you enter the loop-de-loop? 24, because you're at the same height, which is at the very bottom, right? So you've given up all your potential energy into kinetic. And then as you start going up the loop, by the time you pass the side, right, you're level with the center, how fast are you going right there? 20. Then you slow down to 14, back to 20, back to 24. Let's say there was a horrific roller coaster accident and you just fell off the side. How fast are you going right there? 14. How fast do you slam into the ground?
24.
24, right? It's just trading height for speed. The normal force, the only thing that the normal force does for you is guide you into a loop-de-loop path instead of just falling straight to the ground. But because it always acts at 90 degrees to the motion, it never makes you go faster or slower. The only reason we go faster is because of gravity. And gravity is very easy to account for with potential energy. You just track the height. So hopefully this kind of shows you just how powerful the energy method can be. Some crazy loop-de-loop shape. We can easily calculate the speed if we can only figure out the height. Are there any questions on that before I continue with the next idea? Okay, so we need to be able to include other forces. Gravity is the only thing that's allowed to do work at this point. We can throw in things like normal force for free, but how about friction? Friction is obviously a huge thing that we don't want to exclude, so we need to figure out how to work friction in here. Let's take a look at that. So I'm going to compare gravity versus friction. There's some really important differences with the way that these two forces behave. Now, if I were drawing a side view of a ball going up into the air, I could, of course, imagine it slowing down as it goes to the top of the flight. And, of course, one of the ways we could say why does it slow down is because gravity pulls against the motion, does negative work, and removes kinetic energy. And if something is rising, the displacement is upward. Of course, gravity is, of course, always downward. So gravity is pulling at 180 degrees. Does negative work. But if I draw this ball falling back down, of course I can say gravity does positive work on the way down. Gravity hurts you on the way up, it's going to help you on the way down. So gravity does positive work, and it adds kinetic energy. So everything that it taketh away, it giveth back. Okay? So yes, it takes away energy, but then it's ready to give it back. And so it makes sense to say it just got sent to this stored energy account from which we returned it. So it makes sense to say that there is such a thing as gravitational potential energy. You put it into storage because you can get it back, right? You go on vacation, you give your houseplants to a friend, you can get them back. Okay? It makes sense to say that they went into storage. Now let's try this out with friction. Now for friction, I'm going to do a top view of an object sliding along a table. So let's take this eraser for instance. So I'll take this eraser, I'll slide it down the table. I guess I can do it over here. Slide it down here. Does negative work, right? Takes away that kinetic energy. Is it going to come back? No. Okay. So if I draw that block sliding across the table, friction does negative work. And again, removes kinetic energy. But to say that it's in storage is actually not correct, because to say that it's in storage is to say that it's going to be able to be retrievable. Now you might say maybe it just needs a little extra help. Well, if I go like this, friction does more negative work, right? I'm putting more kinetic energy in the system and it's taking that too. Okay? So not only does it not move back spontaneously, but if you give it a little extra push, friction does more negative work and removes that too. Friction does not do negative work going one way and then positive work going the other way. It doesn't take away and then give it back. In fact, it's always taking, never giving back. It's an energy thief. Okay? So to say that energy goes into storage is like saying someone breaks into your house and steals your stuff, that it's in storage now. You can't get it back, so it's just gone. Okay? So the whole idea of potential energy makes no sense whatsoever for friction. To say that the energy is potential or stored is to say that you can somehow get it back. Does anyone know where that energy goes?
Heat.
Heat, that's right. It gets sent to a more disordered form. It goes to those molecules jiggling around randomly. And them reordering to all go in a single direction is not going to happen. If you know from chemistry something about entropy, right? The idea that if you take energy that's more ordered, all of those atoms moving together, and send it into more disordered, which is heat, you're not going to get it back. You've sent energy from a more ordered form of all the molecules of the object moving together as kinetic energy into heat, which is, in a certain sense, kinetic energy, but more random and more microscopic. Okay? So it's not like the energy is completely gone, but you now have sent it somewhere where you cannot retrieve it. So, what do we do for forces like this? Now, I should mention that gravity and friction are just the flagships for these two categories. Some forces, you can say that they go put energy into storage. There are many other forms of potential energy. And then there are forces where you cannot say the energy goes into storage. Names for these kind of forces are, they're called conservative forces. Gravity is just the flagship example. And friction is an example of what's called a non-conservative force, which we abbreviate NC. I'll show you some other examples as we go along in the course. Other examples of conservative forces where you can define a potential energy that you send energy to, and of course, importantly, can get it back. And I'll show you other examples of non-conservative forces where they're going to take energy and you're not going to get it back. But for the moment, we have to figure out how we're going to modify our energy method so that these new non-conservative forces can be dealt with. And the answer is for how we do that is a bit of a cop-out. We just take the equation and put a other crap term in it. So it's just like, here's some other stuff that we're not going to worry too much about in this class. We're just giving an option for that to be possible. So here's what we're going to do. This whole scheme, we're largely going to leave intact. The only thing is that this E, rather than standing for all forms of energy possible, we're going to define E more narrowly. Okay? E, we're going to call mechanical energy. Mechanical energy is going to be a subset of energies. It includes all kinetic energies and all potential energies. And the reason why it's called mechanical is because this is associated with the mechanics of the object, right? In other words, things we talk about in this class. This is basically mostly a mechanics class. Things like how fast is it going, how high is it? Those are things based on how fast it's going, where it's located. Those are the mechanics of the object, okay? But there are other forms of energy too. Other non-mechanical forms. So E does not stand for total energy anymore. It basically stands for mechanical energy, which is a subset of energies we care about in this class, at least enough to want to write down the equation for it. And in fact, the conservative or non-conservative, those terms that we mentioned, you might wonder why they're called that. Of course, they don't mean conservative or non-conservative of all energy. There's no such thing as something that can destroy energy, right? Or create energy. When they say conservative or non-conservative, they're actually referring to mechanical energy. So whether or not something keeps the energy mechanical or a non-conservative force takes it or brings it in from these other forms. So here's a way to visualize it. Here's our house. This is the Physics 210 house. Everything that lives under this roof is E, mechanical energy. We have kinetic energy. We have one form of potential energy so far. Gravitational, lives upstairs, no pun intended. Okay. There will be other residents that we're going to invite in later. And what we call conservative forces are ones that trade between roommates. So we're going to find all the energy in our house somewhere, even if it's traded amongst the roommates. But we do have a door. Sometimes the door gets left open. And then we're at the big wide world of all sorts of other crazy energies that we may occasionally have to acknowledge are present. One of them we already acknowledged was thermal energy. Friction, on a cold day, you can take the kinetic energy of your hands in motion and turn it into thermal energy. That's a non-conservative. So anything that trades outside the house is non-conservative. And of course, the problem with friction doing negative work and trading with this energy form is that you can't get it back. It's not a two-way street. This is never going to come back to this. So you can see we're trying to make it so that our roommates share. They share and share alike. They give you stuff, they take stuff in equal proportions, right? Everything in our house is two-way streets. If someone is going to not only take energy and never give it, we don't want it as a roommate. It's going to have to be out here. Okay? So here is our energy expression that we're going to use. This this is our energy method final form. So here's what we have. The initial mechanical energy, that's the count of kinetic energy and potential energy to begin with. We're counting up all the energy forms that live in our house, we're familiar with, we have equations for them. But if we add them up at the end, and we don't get the same number, it's not time to stress out, because this is the in and out valve to other energy forms, other non-mechanical energy forms. So this is basically our term in our equation that allows us to have some energy coming in or going out without really stressing too much about the equations. So an example, for instance, would be when the non-conservative work is negative. So what we have is the initial mechanical energy. This is going to be negative, so the final is going to be smaller. So E final is less than E initial. That's not time to stress out. We know, for instance, for example, friction is a common example where we send some kinetic energy into thermal. We kind of have a conceptual sense of where it went, but we're not going to chase it down. We're just simply saying is that if we had 50 joules of mechanical energy at the beginning of the problem and at the end we only have 40 joules, well, 10 joules went to heat, right? No big deal. We're not going to try to chase it down. We just kind of acknowledge that it went somewhere. Let me give you another example. You can have non-conservative work be positive, in which case the energy at the end, the mechanical energy at the end is more than at the beginning. Let me give you an example of that. I'll take this eraser, okay? Put it on the floor. So this eraser, if we call the zero of the potential energy at the floor, how much potential energy does it have right now? Zero. How much kinetic energy does it have? Zero. So how much mechanical energy does it have in total?
Zero.
Zero. Has none. Okay? I put it over there. How much kinetic energy does it have right now? Zero. How about potential energy? Got some now, right? What happened to the mechanical energy?
Equal to.
What happened to this total? Increased. Normally, if I throw a ball up in the air, this can only increase if this decreases, right? I throw it upward, it gets more potential energy, but it has to come from kinetic energy. That's not what happened here. This, it gained potential energy, but there was no kinetic energy at the beginning to give, right? It started at rest and ended at rest. Where did that energy come from? Do you have a question back there? No? Where did that energy come from?
Another force.
Right, which was from what? Me. Where did I get that energy that I could give it to that racer?
Chemical.
Chemical. Breakfast I ate this morning, okay? So, here's another form of energy that we should probably acknowledge, chemical energy. We don't want to invite that in. We don't want to have to deal with a formula for that. That's not going to be involved with the mechanics of the object, right? Location or speed or something like that. Forget that. So that's another way for energy to be traded outside of our house, but now it's coming in. So that work was positive. Now, let's not be too hasty. Maybe it would be a good roommate, so let's check it out. So I spent some energy lifting it up there, right? So some of my breakfast cereal energy is gone, okay? If I put it back down, am I full again? No, right? So I expend energy to get it up there, and I give it to the eraser, but I also expend energy putting it back down, right? So it's a one-way street again. There's nothing I can do to get out in the outside world. If I'm expending energy, putting energy out there, there's nothing I can do to reverse it and get it back, right? It's not reversible. It's not a two-way street, so we can't talk about potential energy in the same way. Gravity, it always takes away and then gives back. It's a simple two-way street. It's a good roommate. Chemical energy, we're not inviting in either. This we can't put back here. So you notice that anything that's more complicated, a more complicated energy trade, where it's not a two-way street, those don't make good roommates. We don't invite them in. We don't deal with them in this class at all in any kind of real way, except when we're just trying to figure out why is our balance sheet off. Why is it that our KE plus PE at the beginning and the end is different? It's not time to panic and think that you have created or destroyed energy. We should probably, at least on a conceptual level, acknowledge where it came from. So here an example would be an applied force. This could be from a human. This could be from an engine. It's taking chemical energy and putting it into something mechanical, say kinetic energy. Putting it directly into kinetic energy, of course, would be like throwing a baseball, right? I take chemical energy and turn it into kinetic energy with a baseball. Now, because I happen to lift my eraser upward, we didn't see the eraser going faster because gravity then said, yoink, I'll take that and I'll turn it into potential, right? So the chemical energy came in and then went straight into potential. So if I lift this, the chemical energy is not really going into kinetic energy. It's going faster. It's being stolen to potential, right? It's being put into storage. How do I know? I can get it back. But it can go from potential back to kinetic, but can't go from kinetic back to chemical, right? That make sense? So that is how we finally end up with the energy form. Of course, our previous incarnation of it was when there happened to be no non-conservative work, and then of course you can count on your mechanical energy being all there at the end as the beginning. So again, I mentioned later on in the course we'll find other forces which are conservative forces, therefore we can create a new potential energy out of those. And we'll find some other forces which are non-conservative, and they're going to have to get lumped into this category. Now, as far as how to actually execute a calculation, this is actually going to be the synthesis of the energy stuff we just talked about, and then the work stuff that you learned back in the end of the previous homework. So if you're wondering why I was making you compute all these works just to switch over to computing energy, well, this has still got to get computed the old school way. Okay? So let me show you an example. So let's go back to that loop-de-loop problem I just did. We'll put a little bit of an ending here, though. We'll put a friction patch. We'll put a friction patch, and let me give you some of its properties. It's going to be 20 meters long, and the coefficient of kinetic friction is going to be 0.5. And what I want to simply ask is how fast does this object exit the friction patch? And I guess I'll call that point B, since I already labeled points A, B, and C. Exact same problem I did before. Start off at rest up here. 30 meters. And let's take an example of how we might do this calculation. So here's the general gist. I marked off 3 points before, A, B, and C, in addition to the initial point. And I was sure that I could have all the mechanical energy accounted for in all of those. There's no friction yet, and so the energy is going to have to be in kinetic or potential somewhere. But we're going to lose some going over the friction patch. And so some energy is going to be sent to thermal, and it's not going to be in mechanical, so our count at the very end is going to be smaller. So let's go ahead and do it. I'll tally up, I guess I'll start with my initial, and I'll compare it to my final. Here's what it looks like. My initial energy plus the work non-conservative, in this case friction, is going to be my final mechanical energy. So I'll go ahead and put this in. I already decided that this was all potential. There's zero kinetic energy there. I guess I'll put in the 0 here just to remind you of that. At the end, it's all kinetic. Of course, I'm at 0 height, right? Now before, I was able to count on this energy being all there in this other form at the end. In fact, that's what I did for point C. So all the energy here is got to all be all the energy here. But now, of course, I don't get to have it all. There's going to be a tax for going across the frictional patch. And I've got to compute that tax the old-fashioned way. Size of the force, size of the displacement, cosine of the angle between them. What's the angle between them? What is it? Not 90. So I'm sliding to the right across the friction patch, and friction acts left. Always 180. It's always exactly against you. Cosine of 180 is -1. There's your negative work, right? It's going to take away from kinetic. So we'll put the -1 out front here. UK times N, that's the normal force, times the displacement. We've got to borrow a little cup of sugar from Force's method. Remember that formula? We also need to now go borrow some eggs. So remember the normal force across the friction patch would be what? mg, right? Just a flat surface. So let me put that over here. That's going to be minus mu k mg delta x. Let me just solve this here for you real quick. Here's my initial energy. It's all potential. Here's my amount that's going to be irrevocably taken away to heat. And then whatever's left is now kinetic. The m's cancel. If you can work an m into the non-conservative work term, then you can cancel it. You can't, of course, cancel it until it's in every term. Solve for the final speed. And that final speed, make sure you can get, is 20 meters per second. Of course, you were given UK, you were given delta x, you're given the initial height. So you're going 20 meters per second after you've slid through there. Now, it may not be obvious, of course, that you've lost energy, because, of course, you're going faster than the initial point, but a more informative point would be to compare right here. We're going 24 meters per second, which we found before, going into the friction patch. So you've definitely slowed down, right? You've slowed down, your kinetic energy has decreased, but your potential energy has stayed constant. So obviously the sum of those two is not the same anymore. Where did the energy go? It went to thermal energy. So again, the total energy has, or the mechanical energy has decreased. because you've sent some to eat. Okay, so that will take care of 99% of your current homework. I still need maybe 5 or 10 minutes on Wednesday, but that'll do it for today.